Hello, Bess and BFST. You're welcome to another session. And this time we are looking at hypothesis testing. I think in our introductory slides, we defined an hypothesis. So now this is the time that we are putting the concept into practice. So like I mentioned last time, that hypothesis testing is all about making a scientific guess or an information guess of what an outcome will be. So one of the greatest cornerstones in scientific method of an investigation, so hypothesis, are those statements that you're investigating. So it is a scientific method of investigation, and it is a clear statement of the problem through the formulation of hypotheses or the statements. So we usually use two statements. One is called the null hypothesis, and the other is the alternative hypothesis. So there are basically three methods used when investigating a problem or when carrying out hypothesis testing. The first is the traditional method. We have the p-value method and the confidence interval method. But for this class, we are basically going to look at the first two, and that is the traditional and the p-value method. So starting with the traditional method, so this is the oldest and it has been used ever since hypothesis testing was invented or formulated. So, and when using this method, these are the following steps. So we start by stating the statement of hypothesis or stating the hypothesis. And like I mentioned, there are always two. We have the null hypothesis that is always abbreviated as H naught, and then the alternative hypothesis that is abbreviated as H1 or HA. So the null hypothesis is that statistical hypothesis that states that there is no difference between a parameter and a specific value. And then the alternative hypothesis, which is always your claim or the researcher's claim, it states that there is a difference between a parameter and a specific value. So we state our hypothesis or the null and alternative basing on the scenario of the research or the nature of the research question. For example, our situation A, a medical researcher is interested in finding out whether a new medication will have any undesirable side effects by looking at the pulse rate of patients who take the medication. So the researcher is interested in finding out whether the pulse rate will increase, decrease, or remain the same after the patient takes that particular medication. And from research, we know that the pulse rate or the mean pulse rate is 82 beats per minute. So therefore, stating her hypothesis, in other words, the null and alternative, the null hypothesis, since the researcher is claiming that the medication will have undesirable, will have side effects. So a side effect can be positive or negative. So meaning, if we want to set the null hypothesis for that case, it will be that H naught, which is the null hypothesis, the mean will remain unchanged. The mean pulse rate will remain 82. So a null hypothesis shows that there is no difference between a parameter and a specific value. So meaning our null states that the mean pulse rate will remain 82, and the alternative will state the other way, that the mean pulse rate will change. So will not be 82. So it can either be less or higher than 82. So the null hypothesis specifies that the mean will remain unchanged, and the alternative hypothesis states that it will be different. So in this case, this is a two-tailed test because we have two possible side effects. The pulse rate either reducing all increasing. So that this not equal sign means we are dealing with a two-tailed. So two possible outcomes can be possible. It can either reduce all, increase. In other words, the question is not directed to one uh, side. Then situation B, if we have a scenario where a chemist invents an additive to increase the shelf life of food. So if the mean shelf life is 36 days, then the hypothesis for that case, so the researcher or the chemist is interested in increasing the shelf life. So therefore the null hypothesis will be that there is no difference. In other words, the mean will not increase. So if it has been 36, it will be less or equal to 36. That is the null hypothesis. Then the alternative will be the chemist's claim or the researcher's claim. He is interested in increasing the shelf life of food. So therefore, our alternative hypothesis will be the mean will be greater, or the mean shelf life will be greater than 36. So to help you understand this more, in simple terms, the alternative is always the claim of the researcher, that which is increasing. You can see the mean will be greater than. So the null is always the opposite of the alternative. So in this case, the chemist is only interested in increasing the food shelf life. So her alternative hypothesis is that the mean shelf life will be greater than 36, and this is called a right-tailed test. You see, it is pointed to one direction. It is only interested in increasing the shelf life. The previous situation was the mean will not be equal to 82, so it can either be less or higher. So, but this is pointed to one direction, which is increasing. So it is a right-tailed test. Then situation C, if we look at a contractor wishing to lower heating bills by using a special type of insulation. So if the average of the monthly heating bill is $78, the hypothesis, so he is interested in lowering, so that will be our claim or our alternative. So it will be that the mean bill will be less than 78, and therefore the null hypothesis for that will be that the mean has always been greater or equal to 78. And remember, with research, you're coming in to solve a problem, so this has been maybe high, so the researcher is coming in to lower the heating bill. So the test is a left-tailed test, since the contractor is interested in only lowering heating costs. So these are the symbols that we are going to be using. We have the equal sign. We are all aware of that. We've seen the not equal to sign. And we've used the greater than, less than, greater or equal to. So greater or equal to, it means if I have greater or equal to 30, it is 30 and above. It means that particular value is also inclusive. Then less or equal to, the same. That particular value is inclusive, then all the others that are less than it. So this works for a one-tailed situation. Then for two-tailed test, we have not equal to. So for the right-tailed test, we have greater or equal to k. K can be any value. Then, so if the null hypothesis is less or equal to, the alternative will be greater than k. Then for the left-tailed test, like we've seen, then the null is always greater or equal to, and then the alternative will be less than k, where k is any specified number. So a statistical test uses data obtained from a sample to make a decision about whether the null hypothesis should be rejected or not rejected. So that numerical value obtained from a statistical test is what we call the test value. So a sample mean is always computed and compared to the population mean. So after doing that, we then make a decision to either reject or do not reject the null hypothesis. Use a basing on the value obtained from the statistical test. If the difference is significant, the null hypothesis is always rejected. And if it is not significant, the null hypothesis, if it is significant, the null hypothesis is rejected. And if it is not significant, the null hypothesis is not rejected. There are always two possibilities for a correct decision and two possibilities for an incorrect decision. So therefore, if you make a wrong decision, you commit what we call type 1 or type 2 error. So type 1 error occurs if one rejects the null hypothesis when it is true. Remember, when the null hypothesis is true, you're not supposed to reject it. When the null hypothesis is true, you do not reject it. But then if you reject it, you commit what we call type 1 error. Then the other error is type 2 error, where in case the null hypothesis is false, you're supposed to reject it. But then if you don't reject it, if you do not reject the null hypothesis when it is false, you commit what we call type 2 error. So the level of significance is the maximum probability of committing type 1 error. So we are not going to zero match on type 2 errors. We shall only base on type 1 error. However, these are related in a way that increasing type 1 error reduces chances of type 2 error, or increasing type 2 error reduces chances of committing type 2 error. And like I mentioned, that common confidence levels are always used, which are 95, 90, and 99. So, and the difference between 100 and the confidence level is always the error. So therefore, statisticians generally agree on using arbitrary significance levels. So these are the error levels. So for 90%, the error level will be 0.1. For 95%, it will be 0.05, and for 99%, it will be 0.01. So if the null hypothesis is rejected, the probability of a type 1 error will be either 10%, 5%, or 1%, depending on the significance level used. So after we choose a significance level, a critical value is selected from the table for the appropriate test. And for the mean, we always use a z-test, and this is consulted to find the critical value, which determines the non-critical region. So the critical region separates the critical value, or the critical value separates the critical region from the non-critical region. And the critical region is the rejection region for the null hypothesis. If you find a value lying in the critical region, then we reject the null hypothesis. So therefore, this is also known as the non-critical region, is known as the non-rejection region of the null hypothesis. So the critical value can be on the right side of the mean or on the left side of the mean for one-tailed test, and it depends on the inequality sign of the alternative hypothesis. And for a one-tailed test, the null hypothesis should be rejected when the test value is in the critical region or on one side of the mean. So for a two-tailed test, the null hypothesis is rejected when the test value is in either of the critical regions. So for a two-tailed test, the critical region must be split into two equal parts. So if we have alpha, then we are interested in getting alpha over 2. And this must be on both the right and the left sides of the mean. So in this case, the area to be found in the Z table, so we shall subtract alpha over 2 from 0.05. Remember, this is always in the tail, so the balance, and therefore the critical values will be 2.58. We've seen this in our Z table. So if we have alpha Now we can use the T table, or even the Z table. So if we are interested in getting, sorry, take it back. So since the critical region is always in the tail, so if we are working at alpha over 2 as 0.0.05, subtracting that 5 will give us an area of 0.49. For the critical value, the Z value that corresponds to that can be got from the Z table. So our area is 0.495. So you look for 0.495, and if it is not there, you look for the nearest. So 0.4, and they are in order. So 0.495, so this is 497. It is 0.4950. 0.495. This is 4943, 4945, 4946, 495. So we can go with 2.58. So that will be our Z value. And it lies in both tails. So one of it will be positive and the other will be negative. So now we are going to look at the procedure for finding. Now remember, that is the test value. We are now interested in finding the critical value. So we always first draw the figure and indicate the appropriate area that we did in normal distributions. And then for one-tailed test, we subtract the area equivalent to alpha from 0.5. And for the two-tailed test, we subtract the area equivalent to alpha over 2 from 0.5, because this is in both regions. Then we look for the area in the Z table corresponding to the value obtained in step 2. And if the exact value cannot be found, we use the closest value. Then find the Z value that corresponds to the area, and this will be the critical value. So determine the sign of the critical value. And for one-tailed test, if the test is left-tailed, the critical value will be negative, and if the test is right-tailed, the critical value will be positive. So we are now going to look at the application. So the formula for getting the test value, which is the Z score, is the observed value minus the expected value, which is the mean, over the standard error. So the Z test, so this is our sample or observed value, the mean, over the standard error, that is standard deviation, over the root of the sample size. So the procedure for testing the hypothesis using the traditional method: you set the hypothesis and identify the claim, find the critical values from the appropriate table, compute the test value, make the decision to either reject or not reject the null hypothesis, then summarize your results. So we are going to look at an example that will make meaning from all that I've said. So a researcher reports that the average salary of junior agronomists is more than $42,000. A sample of junior agronomists has a mean salary of $260,000. At alpha of 0.05, test the claim that the junior agronomists earn more than $42,000 a year. The standard deviation of the population is 5,230 So first step is always state the hypothesis and identify the claim. In other words, we state the null and alternative hypothesis. So our alternative, we start with the alternative, which is the claim. So the agronomist reports that the researcher reports that agronomists earn more than 42. So meaning our claim will be the mean greater than 42. So therefore, the null hypothesis will be that the mean is less or equal to, remember it is supposed to be the opposite of this, it is less or equal to $42,000. So our step number 2 is to find the critical value. So we are working at alpha of 0.05 and the test is a right-tailed test. So therefore the Z value that corresponds to 0.05 can be got from our table. So 0.05, we are going to use our table. Remember that Z alpha, so 0.05. That is 1.645 or 1.6 when rounded off. So that is our critical value. Then we compute the test value using the formula. So we are given the observed salary, the mean salary, and then we have the standard deviation and n. So therefore our z or our test value is 1.3. So now we make a decision on whether we reject or do not reject the null hypothesis. So make the decision. Since the test value, remember our test value is 1.32, is less than the critical value, which is 1.65, and not in the critical region. So now when we look at the diagram, our critical region, the test value marks the critical region. The critical value marks the critical region. So therefore our critical value was 1.65. So anything that is greater than 1, remember the researcher claims that they earn more than that. So anything that is more than 1.65 lies in the critical region, and anything that lies here, we reject the null hypothesis. But our test value came out less, it is not in the critical region. So therefore, we do not reject the null hypothesis. And the null hypothesis said that agronomists earn less or equal, $42,000. So after that, we summarize the results, and there is not enough evidence to support the claim that junior agronomists earn more than $42,000. So in other words, if we had got a test value that was greater than 1.65, then we would reject the null hypothesis and take on the claim. But then what we've got is less than 1.65, is less than the critical value. So therefore maybe the sample that he did and had more than 42, it was by chance, but then there is no clear evidence or enough evidence. So that is it with the traditional method. Then we have the p-value method, and you're free to use any method. So the p-value or probability value is the probability of getting a sample statistic in the direction of the alternative hypothesis when the null is true. So the p-values of the z-test can be found still using the z-table. So here we first find the area under the normal distribution curve corresponding to the z value, and then subtract it from 0.5. Remember that critical region is always in the tail, that's why we are subtracting from 0.5. And now to get the p-value for the two-tailed test, we double the area after subtracting. So decision rule, how do you make a decision when you've used the p-value method? If you get a p-value that is less than alpha, you reject the null hypothesis. And if the p-value is greater than alpha, you do not reject the null hypothesis. So this is still the method, the steps followed, or the procedure, and they are not different. So state the hypothesis and identify the claim, compute the test value, find the p-value, make a decision to either reject or not reject the null hypothesis, and then summarize the results. So an example, A researcher wishes to test the claim that the average age of Year 2 students is greater than 24 years. She selects a sample of 36 students and finds the mean of the sample to be 24.7 years, with standard deviation of 2 years. Is there enough evidence to support the claim at alpha is equal to 0.05? We are supposed to use the p-value method. So we start by stating the hypothesis. So the researcher claims that Year 2 students are greater than 24 years. So this is our claim or alternative hypothesis. So therefore the mean is greater than 24 years, and the opposite of this will be the null hypothesis, which will be less or equal to 24. So step 2, we get our test value using the formula. We have the observed age, we have the mean age, the standard deviation, and then the sample size. So that gives us the test value. Then we find the p-value. So using the Z table, the corresponding area of Z is equal to, or the corresponding area of the Z value or test value will be, so we look for 2.1 in the Z table, 2.1. Okay, the Z table is here. So it is 0.4821. 0.4821. So we subtract this from 0.5 and the remaining area will be 0.0179. The reason we are subtracting is because our region of interest is always in the tail. So therefore our p-value is 0.0179. So remember the decision rule. When p is less than alpha, taking you back here, when p is less or equal to alpha, we reject the null hypothesis, and when p is greater than alpha, we do not reject the null hypothesis. So we are going to base on the value of p to make a decision. So is p greater than alpha, or alpha is 0.05 or less? So since it is less, this is 0.05, this is 0.01. So since this is less, we reject the null hypothesis, and therefore there is enough evidence to support the claim which states that the average age of Year 2 students is greater than 24 years. So that is a brief introductory of hypothesis testing, and thank you so much. Stay well.